All right, announcements. We have an assignment due next week. We have an exam on Friday. The plan is on Thursday, we're gonna do our exam review. So as last time's review session was really good. We filled the whole period, which was excellent. Please come prepared with a few questions. And that will make sure I'm not staring around awkwardly waiting for people to ask me things. And I think other than that, it's really what we have going on here right now. Does anyone have any questions before we get started on new content? All right, so we are in the process of talking about hash tables and collision resolution. Because when two elements map to the same index in a hash table, we need to figure out what to do about them. So the first idea that we were talking about was called linear probing, which says that when we find something already where we want to store the new object, we're just going to continue to look at the adjacent indices. So wherever we're looking, if we call that I, we're going to look at index I+1, I+2, I+3, all of that mod table size. So we loop back around to index 0 if we fall off the end. And this ensures that if there is an open space in the table, so unless the table is full, we will eventually find a place to put this. And this sounds like it would be really bad as the table size, as the table gets full. So what we should talk about are some of the downsides to linear probing and when we might want to do something about that. Just like when an array list gets full, we can resize the array list and then copy over all the elements into the new larger list. We can do something very similar with hash tables. We can make a new table size and rehash all of the values into the new table size. And that will make new adds take less time. So we talked about how to code up linear probing. So we have a particular table size, and this was for maps, not so much for just a regular hash table, but basically we can do a get to figure out is the object at the location that the hash says it is. If it's not, then we keep looking for it. We can do a put, which says, is there something at the index that we'd like to store it at? If not, just store it there. If so, continue to query the next indices until we find a place to put it. And then we found there was an issue with removal. And if we removed something that was to the right of it originally hashed to the left of it, then we ended up with an issue. So in this case, we deleted S, but H originally hashed, I think, to 4. Maybe it hashed to 5. H hashes to 5. So if we look at index 5 and then we look at index 6, we see that 6 is empty here, and that tells us that H is not in the table, which is obviously false. H is in the table, it's just past this element that's been deleted since H was added to the table. So removal was a little bit trickier, and we determined that we could solve this issue by introducing the idea of a tombstone, this Boolean marker that says something used to be here. And what that means for insertion is a tombstone does nothing. We can easily add to an empty cell that has a tombstone because nothing about the tombstone affects the insertion procedure. And the insertion doesn't change later contains or deletion queries. So insertion doesn't care about tombstones at all. Deletion, whenever we delete an element, we now need to turn the tombstone flag on. Which means that when we do future contains, when we're going to look for that H on the prior slide, we're going to see that at index 6, there is a tombstone here, which says that H might still be in the table and we should continue querying until we find an empty index with no tombstone flag. You can imagine that eventually, if you do enough adds and removes, everything's going to have a tombstone. So eventually we end up with an issue where it's kind of like we didn't have any tombstones to begin with, because we have to search the entire table to determine if something is in the table or not. So if we are doing occasional rehashing and kind of resetting of our hash table, this is not a problem. But rehashing is a linear time procedure. So it's something we like to avoid doing unless we need to. It's a one-time linear procedure, so it's not as bad as something like an add being linear, or a remove being linear, or a contains being linear, because we might be doing that very frequently. But if we need to rehash in order to reset the tombstones so that we have an efficient structure again, that seems like it's annoying to do. And we would try to minimize how frequently we do that. So I think this is as far as we got.
You only use a tombstone when you remove something?
Yeah, you only turn it to true. We're gonna read the tombstone whenever we do a contains and we find an empty cell, but we're not modifying the tombstone unless we're doing a deletion.
But you wouldn't put a tombstone if, like, if there was an index that was already empty.
Right.
And never removed from it.
Correct. Yeah, you have no tombstone there because nothing used to be there. If we find that when we're looking for something and we find something with no tombstone, then we know for sure that that element is not on the table. Because if it was in the table, it would have already been found, or this index would have a tombstone and we should keep looking. But if it doesn't have a tombstone, we can stop. Good question. So that was the concept of a tombstone. So the question we haven't really answered now, we've talked about this concept of table resizing, is when should we actually do a table resize? As the table fills up, you can imagine it is full. Doing any kind of contains or add or remove will take linear time. The average number of cells that we'll need to look at is the table size over 2. Because at this point, they're going to be randomly jumbled in the table. The hash really will have done nothing for us, and we're just doing a sequential search. It's like we don't even have a hash table. It's like we're starting at index 0 and just searching for it. So we don't want to let it get there. We don't want to let the table fill up. As I mentioned, if we resize the whole table, it's a one-time linear time operation. So not as bad as a frequent linear time operation, but it's still something that we would like to avoid doing unless we need to do it. But what do we think? When is the best time to grow and or shrink the table? If you were in charge of this, setting up this rule, where would you place that and why? Yeah.
Just whenever you add or delete something.
So if we do it every time we add, it turns add into a linear time operation. If that's the case, then we might as well just use an array. If we do it every time we remove, then it's kind of the same thing. So we would like to have constant time adds and removes. We would like to determine when does it really shift from being a constant time operation to being a linear time operation. Because when the table is empty, you go add, you hash it, and it goes right where you want it to be. When do you look an average of one place? So let's say we have a hash table of 1,000 elements. And how full would the table have to be such that on average, I go to hash something, there's something there, but the next place I go to look is free. On average. Yeah, it's halfway full. How full would it need to be an average of 4? An average number of operations, like I look here, and then that's 1, 2, 3, and the 4th place is free. Yeah, it's about 3/4 full. So at about half and at about 3/4, we're still reasonably constant, but that's also on average. What we see if we're using linear probing is we get clumps of data. So there are large places of free space and there are large places of clumps in the data. So while we might get an average of 2 operations or an average of 4 operations, the deviation of that is actually quite large. And so sometimes we'll go to add and it will be very fast, and sometimes we'll go to add, it'll be a little bit slower. So we figure that at about the half full point, if we reach more than half full, it's time to grow our table. Because a reasonable number of our operations are gonna start taking some time proportional to the size of the table. And it would be better if we had twice as much space. We would go from half full to a quarter full if you double the size of the table. And at a quarter full, we can add as much data as is already in there again before the table is half full again. So that is nice. So when the table is half or more full, the average store retrieved takes 2 operations. When should we shrink the table? Should we ever shrink the table? Would it make sense to do that at some point? The 4th full? If we choose 1/4, how full is the table when we are done? Half. So what happens if you add when it's half full? We resize again, and then it's a quarter full, and then if we remove, we resize again. So it's a really good idea, but we get caught in the middle of this. We want to resize with every operation if we're unlucky. So while that is probably mathematically the right answer, we end up going with 1/8 just to make sure that there are enough operations in there that we don't have we aren't resizing the table all the time. So 1/8 or less full. If you cut the table size in half, now it is 1/4 full. We're still constant in terms of our average add and remove. And we save half the memory that we are currently using. So these are just industry recommendations or industry standards for how full our table needs to be when we resize it. What actually your needs are will vary project by project. So this isn't a hard and fast rule. It's just if you don't know better, use this. If you don't have a reason to modify this, use this, and you can't really go wrong. Do note though, that you change the table size, the hashing indices change because the table size has changed. So the base that we are using for our modulus has changed, which means that the index that we would hash to also changes. So we need to rehash all of the keys in the table, which is what makes it a linear time operation. If we have half the table size full of data, or 1/8 of the table size full of data, it's still some proportion of the table size, which makes it linear. Questions on linear probing or the concepts behind linear probing? Like I mentioned yesterday, we're gonna get a little bit of experience with this after I introduce the next thing, so we're gonna have an exercise here momentarily to do some stuff with it, get a little bit of practice. No clarifying questions? All right. I do want to mention and go into a little bit more detail about clustering, which is you have randomly placed data, right? We would expect it to be uniformly hashed. When we go to hash something, we expect that it's going to hash uniformly across the entire table. Why might we see clustering? Why would clustering make sense in our data?
It's like we're allowed to fly stuff.
They're clustered together. So if we had a table of size 1,000, we would see eventually a lot of data between some index I and maybe I plus 50. There'd be a lot of data right there. And then there'd be other chunks of data that are all clustered together, and then other places where there are large swaths of free space. With maybe a few things inserted in them. I think to intuitively understand this, it makes sense to draw out a small table. Or using this pen. So I'm going to use a fairly small one here to talk about why it is. We'll use a table of size 7 because it's a prime number. We have index 0, 1, 2, 3, 4, 5, and 6. I have some number. Let's say we're just going to use an integer and we're going to hash that integer into the table. Someone shout out an integer. 17. What is 17 mod 7? 3. So we would want to store 17 right here. We would expect that whatever number comes next should be equally distributed among this. The fact that this first number hashed to index 3 doesn't bias the next number to not hash the 3. Right? They're independent events, just having the next number. So how many different, if these were evenly distributed, let's say we have the same number of numbers that hash to each of these. Let's say there are 100 of them. Just for evenness sake, there are 100 numbers that would hash here, 100 numbers that would hash here, 100 numbers that would hash here. Great. Where are we, how many numbers would get stored in each of these indices with the next hash? All 100 of the numbers that get hashed to 0 would get stored in 0. All 100 of the numbers that hash to 1 would get stored in 1. All 100 of the numbers that hash to 2 would get stored in 2. All 100 numbers that get hashed to 3 would get stored in 4. All 100 numbers that would get hashed to 4 get stored in 4. So we're starting to see a bias toward the next elements being stored in index 4 and not elsewhere. So it's no longer an even distribution of where we're going to store the next number. There's a slight bias toward being after something that's already being hashed. So this is why we see clustering in practice. That slight bias, when we add and remove hundreds of times in a large table, creates clusters of data, even though we have a uniform distribution. Does that make sense? It doesn't take very much to see it. You just have to see that, sure enough, multiple index get mapped to a single index now. So we're more likely to put something here than we are anywhere else in the table. Let's say that happens. Let's say we hash something again that has index 3 or has index 4. And we hash, I don't know, 4. Now we have the 100 here, 100 here, and 100 here, all hashed now to 5 after linear probing. So we start seeing that it gets more and more likely the bigger the cluster is. So new keys are more likely to hash into big existing clusters. So we see things that now hash into clusters. So it's just something that we need to deal with. And sometimes in industry, you will find yourself doing things like if you get a reasonably large cluster, change the table size and rehash. And that can remove some of the clustering. The easier solution to linear probing that we talked about last time is called separate chaining, where we're going to use linked lists at each one of these indices. So now instead of there just being an index that is an array element, a single integer or a single type T, whatever it is that is being stored in our hash table, we're going to replace each index with a linked list. As we do this, when we find a collision, we just add it to the linked list rather than try to modify the index. So we don't really need to do collision resolution. We're just adding to an existing linked list. So no linear probing needed. What are some of the downsides of separate chaining? We wouldn't introduce linear probing if that weren't the answer sometimes. Both algorithms are used in practice because they have different pros and cons. Separate chaining seems like it's just strictly better at first glance. The main downside is requires even more memory. Instead of having just one array structure, each one of them is a linked list structure. So it has a head pointer. We probably don't really need a tail for these linked lists. We're not really accessing the tail very frequently. But it still needs a head pointer, it needs a size, and then it needs a number of nodes equal to the amount of data that's stored there. Hash tables already take up quite a bit of memory by their nature. We have way more memory for storage than we have actual elements that are there. But it can certainly save you some time. Because instead of resizing the table, you don't really ever have to do that. Unless your longest list gets longer than you are willing to tolerate. Because now you actually have to go search a smaller list. So as soon as your either average list size or longest list size no longer becomes constant in terms of the size of the table, but it starts to become proportional to the size of the table. Now you might consider making a larger table and rehashing everything into smaller lists to potentially have the searching time that it takes through your linked list. If you can imagine your average list has 20 elements in it, now you're searching a list of 20 things sequentially every single time you're adding, removing, querying, contains, any of that. So separate chaining is certainly easier to implement, but definitely requires more memory. And it's not quite as fast if you have a very small amount of data in your table. It lives, the element lives directly at the index in a linear probing hash table. And what you have is the either head of a linked list or a dummy head of a linked list at each node. So you may actually be doing a search followed by a search, even if there's only a single element in there for a linked list, especially if you're using a dummy head. There have been significant numbers of additional solutions that all use these two base same ideas that you should be aware of. So two-probe hashing is an example of what's meant to minimize the number of collisions. So instead of hashing to a single location, you hash to two locations. You have two separate hashing functions. And you will hash to whichever one has the shorter of two linked lists at that location. You can also hash to two separate structures that are just mirror copies of each other, except they store different data. So two different tables, you would say this hashes to 4. I now have two structures. I'm going to go search through the list of one and search through the list of the other. But you can then query the size real quickly and insert into the shorter of the two. And that keeps you from having to do a table resize. If you've already kind of gone through that. If you do this, the theoretical guarantee that you get is the expected longest chain goes from the log of the table size to the log of the log of the table size. You can use double hashing. So that's two probe hashing. Double hashing says we're going to use linear probing, but rather than skipping one ahead, one ahead, one ahead, one ahead, we're going to use some kind of predetermined sequence, like the quadratic formula. So 1 squared is 1, 2 squared is 4, 3 squared is 9. If you look ahead and you find something already there, then you look ahead instead of 1 space, you look ahead 4 spaces. And then you look ahead 9 more spaces, and then 16 more spaces. And what you guarantee when you get this is that clustering just goes away. Or your clusters aren't quite as large. So this is the exact same as linear probing, except now we've removed the concept of the issue of clustering from what we need to consider. Additionally, the table can become a little bit fuller before we need to resize. Those all sound like pros. Why did we bother to learn linear probing in the first place? And the answer is deletion is a major headache. So you just straight up don't even really want to think about deletion in this system because you need some kind of tombstone, but it's really hard to tell whether something is still in the table or not from that point because you've lost that guarantee of, well, I can just continue to look past it. You come upon a tombstone, you don't know when that tombstone was generated. So you don't get a guarantee, even if you see a tombstone, that the thing isn't in the table. So you need something more complicated to deal with deletion that we just don't have time or interest to go over at the moment. Questions on either of these alternative solutions? All right, let's do some practice. So just like I drew an array of size 7, I'm going to have you draw an array of size 7. We are going to start out using linear probing collision and insert the following integers into this array of size 7. Since they are integers, you're just going to use their values as their hash. So insert 10, 1, 8, 15, and 14 into your array of size 7, your hash table of size 7. Where do we want to put 10? You guys 3, 10 mod 7 is 3. So we're gonna put 10 right there. Where does 1 go? What? Where does 8 go? Would also go in 1, but since we're using linear probing, where do we actually put it? 2. We just move to the next empty place to put it, so 8 is going to go here. How about 15? Where does that want to go? Yes, so it wants to hash to 1 because 15 mod 7 is 1. There's something there, there's something there, there's something there, there's something there. So 15 now goes here. And we're starting to see this whole clustering thing happening already. Where does 14 want to go? 0. 0. So this is what our hash table should look like after those insertions. We have an empty 5 and an empty 6. Go ahead and trace contains on 15. How would we locate, determine, is 15 in this table, yes or no? Algorithmically, how would we do that? Anyone with ideas? How do we trace contains on 15? So we are first going to hash it. 15 hashes where? To 1. So we're going to ask, is the value that's stored at 1 equal to 15? No. Is it empty? No. So we're going to look at the next element. Is what is stored at index 2 equal to 15? No. Is it empty? No. Not equal to it, not empty. Hey, look, we found it. We're going to return that it's in the table. What if we wanted to trace contains on 12? Let's do one better. Let's trace it on 11. Yeah, if we're doing the mod 12, we'd start at 5, 11 would start at 4. So 11, we're going with 11. 11 starts at 4. We would ask, is this thing 11? No. Is it empty? No. No. We would move forward. Is this equal to 11? Is it empty? Yes. Now we know 11 is not in this table at all. We don't have to search anywhere else because if 11 were in the table, it would be at the place it's supposed to hash or somewhere before we reach an empty. Granted, an empty without a tombstone, but we haven't deleted anything that requires us to think about that. So it'd be exactly the same for 21. 21 would hash to 0, and we would now do basically a linear search. But I wanted to show that for some things we can actually save time. And so there are things that will hash somewhere either directly that's empty. If we hash 12, we would immediately see this place is empty. There's no tombstone, so it's not on the table. We can, if the table is not very full, we can answer these questions very quickly. But as the table starts to fill up, you can see that hashing something like 21 and asking if it's in the table is exactly the same as a sequential search through an array. It doesn't actually save us any time to have done any hashing whatsoever. So this is more than half full, we should have rehashed already. Let's trace delete. So delete wants to delete 1. How do we do it?
Phrase, right, it's modded, shove it one, it's not there.
Yeah, so one is here, so we're gonna hash the one that we want to delete, find that it's at index one, and index one is in fact one, so we found it in the table. So now we can just remove it. But we also need to add a tombstone to it. Because now something used to be here. And something like 8 has become inaccessible without the tombstone. Because that also hashed to 1. So I don't know, with my second grade drawing skills, I'd really like to draw like a skull and crossbones, but even that's beyond my artistic ability. So I'm just gonna put an X. I know that's boring. But pretend that's a skull and crossbones, it looks really cool. So how does the fact that this has a tombstone, how is that gonna affect future contains calls?
Skip over it, right? Like,
Yeah, skip over it if it's a contains. Or if it's a delete.
How is the tombstone recorded in a text in?
So usually you have an object that's stored there. Yeah, so the object that's gonna be stored in each one of these would be an array list of type. Some custom object, where you would have a two-part object, where you have the integer, and then you have a boolean.
So in this case, it's an array of integers, is there a special way to do that?
You have to create a custom object.
We probably check to see if it's tombstone. And then just click, right?
Yeah,
That would be there, and it's not.
so if we did a contains on 8, we would hash 8, get 1, see that this is empty. It doesn't have an integer associated with it, but if you look at the boolean field associated with it, you would see tombstone is true. So that tells us something used to be here, we should look past it to see if we can find it.
Does that become a call after the is empty then? So is empty.
Yeah.
Then we say is tombstone.
Yeah, exactly.
How many times do you look with the tombstone? Like if the thing's totally full, you just cycle back to the first tombstone?
Yeah, you usually have to go through the entire table, which is why we absolutely want to rehash at some point. We want to minimize the number of linear time operations, but they're going to become necessary. Otherwise, everything becomes a linear time operation if the table gets too full. Better to have a one-time linear operation followed by a bunch of constant time operations than approaching everything is linear. So yeah, usually you're going to have some kind of object that just has a field for the tombstone flag. If you were making this as an object, you would just have two fields. You have something like an int value and a boolean tombstone. In your constructor, you pass the value and you set the tombstone to false.
So, the third, I guess, do you find a tombstone, but you just check it, then do change space, or you say?
Yeah, you find an empty space with no tombstone, then you can quit. And if it's an insert that you're trying to do, you don't care that there's a tombstone there. When you insert there, you do want to switch the tombstone flag though back to false. I guess it doesn't really matter. Once the tombstone is set, the tombstone is set. But if you're gonna rehash, then every tombstone needs to be set to false. So maybe you do want to set it to false anyways. It just creates less future work. So we did all of this with linear probing. Go ahead and start back at the top. Oh yeah, question.
So what was the answer to that question?
To future contains calls,
Yeah,
we basically just treat it like there's something there that doesn't match.
so it doesn't affect the draw.
Right,
Oh,
yeah, this is a full space that doesn't match anything with regards to contains. So if we wanted to call contains on 8, we would now go here and say, is this value equal to 8? And so the answer is no, it's not. The tombstone flag is on. And then you go to the next one. You don't quit because it's empty, but it has a tombstone there that allows you to say, continue looking, it still might be empty. Question? So start back at the top and do this all over again with separate chain. Rather than linear probing. So we're going to have each one of these elements now, instead of just being a place for an integer, it's the head of a linked list. So you can think, if we're gonna use dummy heads, that basically I'm gonna rewrite these indices, I'm just gonna redraw them. Each of these are now objects that are null. Or at least that the head is null. And as we start adding to them, we're gonna start adding vertical linked nodes. As things hash to the same location. Or wherever they end up hashing, we're just gonna add them to that linked list.
You want to put them in shorter list.
If we're doing double hashing. Right now, they're just gonna hash to a particular location. So they're added to the list at that location. It's usually added to the beginning because we don't actually have a tail pointer for any of these, so we have no way, we don't want to have a linear time operation with regards to the size of this list. So we're just gonna add it at the head, which is gonna make it more difficult to draw, but more efficient from the computer's perspective.
Let's have its own like current node.
Yep. Well, I don't think we even need a current, I think all we need is the head. Head and size. But yeah, each one is a separate linked list. So if you were to make one of these objects, you would have. An array list of linked list of node. It's kind of like a 2D array. Think of it kind of like a 2D array, except now we have different types of lists in each axis. In this horizontal list, we have an array list. And in this vertical list, for each element of that, we have a linked list. And each element of that linked list is a linked node, or a node in this case. So if we wanted to insert 8 from here, if we only had access to the head is going to point to this node. We don't have access to anything that would be past that. So we're going to be adding to the front of this list, which says break this connection, make a point to the new node and point that node's next to what used to be the head. You stored off the temporary head. So we're going to basically do that. We have a first node here that is 8 pointing to another node that is 1 pointing to nothing. That next is null. And we do the same thing for 15 because 15 also maps to exactly the same thing. So we end up with the new head is 15, next 8, next 1 with a null pointer. And then 14 map to 0. So separate linked lists for each index. We will see that it looks a little bit different. So the question I have now is, what was better here and for what? Linear probing versus separate chaining. What are the pros and cons of having used linear probing to solve this problem? What are the pros to using separate chaining? Yeah, it's always going to be constant because we're always adding it to a linked list. What about remove?
Like quadratic for remove with the array and linked list one.
So it should be proportional to the size of the linked list. The longest the linked list could reasonably be is linear, the number of nodes that have been entered. So there's no reason it should be worse than linear, but it might approach linear if everything caches to the same location. But that would have been the case with linear probing anyway. If everything cached to the same location, then they would be one large cluster of data where everything would have happened, and you'd have to be doing the same searching element by element as you would next.
The remove just would be a tombstone, you just have to make sure you minus the size or.
Yeah, you just change the associated size of each linked list. You can see this takes more memory though, because before, all we needed was this table. And now we need this table plus all of these nodes for all of the data as well. So the main downside of separate chaining is the additional memory you need. What about contains? Kind of the same thing? How would you go about rehashing? What would a rehashing algorithm look like? If you had linear probing, you would just make the new table object, go through this original table from start to finish. Is there anything here? Is there anything here? Is there anything here? Is there anything here? If there is, hash it into that structure, delete it from this structure. With a linked list, you're going to ask, is this null? If not, iterate through this list. For each element, rehash it within the table. So it's basically the same thing across both. We don't have to worry about tombstones with separate chaining, which is nice, but at the same time, it takes just about twice as much memory. Doesn't change the order of the space requirement, it's still linear, but that could be a problem on some machines. It's at least worth considering. That is all I have for you on hash tables for the moment. I will be getting you some kind of assignment for that eventually, but I want the current assignment that you're working on due. I want you to have finished the exam, so some more experience with this will be coming at some point in the future after your current grades are passed. I will see you tomorrow, and we're gonna start talking about advanced sorts. And office hours starting now, if anyone has questions on homework or exams.